So to finish this unit, we're going to talk about the systems of inequality. So we've been talking about equations the whole time, and we're going to talk about what it looks like graphically. So returning to something we learned in the previous unit about how to graph an inequality, okay? We are going to graph two inequalities. So we're going to graph them just like normal, okay? So you see here, we've graphed y is greater than x plus 2, so that was graphed here. So we graphed the line y is equal to x plus 2, but remember, just as a refresher, because there is no or equal to, we make it dotted. And what happened is that this one ended up shading this way, shading it up. Then we also graphed y is less than or equal to negative 2x minus 1. Remember, this one would be solid because the or equal to piece. And we ended up shading down to the left. So when we're talking about a system, right, we're talking about multiple inequalities in this case. Our solution is going to be where the two shaded regions overlap. So our solution will be the purple here. And in general, what you're going to write in there, just to be absolutely clear, is a big S. And that stands for solution. Okay, so any point that's within that shaded region in purple that we put labeled with an S, any point is part of our solutions in this case. So it's a little bit different than equations where we get actual numbers. In this case, we're going to get a general region of points that all are part of our solutions. If we take a look at the next one, x plus y is greater than 4. We have the line x plus y is equal to 4, but we make it dotted. And it's shaded up to the right. Then we also have the line x plus y is less than negative 1, once again, also dotted. Okay, but that's shaded down. And you notice there's no overlapping region here, right? So in this case, we would have no solutions. Okay, so if there is no overlapping region, then our answer would be no solutions, because whatever x and y value or points we pick need to work for both in this case. So let's take a look at how this will work in a few examples. So for the first one, try to color code this. We're doing y is greater than negative 2x plus 2. So I'm going to just think about this in mx plus b form, knowing that this is going to be a dashed line or a dotted line. Okay, we use dotted above. Let me change that. Okay, so the plus 2 will be our y-intercept. Our negative 2 is our slope, so negative 2 over 1 we could think about. So that's down 2 to the right 1, or up 2 to the left 1. And we're looking for that dotted line. Okay, I'm going to label it y. I'm going to use the actual inequality itself as greater than x plus 2. All right. Remember, we had a little trick here. If the inequality is opening up towards the y, then the y itself that's on the labeled axis is in the shaded region. So we would shade this way because the inequality is opening up towards that. But you could absolutely also test a point. And we said the easiest point to test was 0, 0. Those are x and y values. So if we plug those in for x and y, we could say, well, is 0 greater than negative 2 times 0 plus 2? Negative 2 times 0 is just 0. So is 0 greater than 2? The answer is no. So 0, 0 is not the point. So the origin is not a point in our shaded region. So we should shade the other way. The second one is going to be a solid line, right? Same idea. We're going to take x plus 1 and graph it. So 1 is our y-intercept. And our slope is 1, which is up 1 to the right 1. Or it could be down 1 to the left 1. Remember, it's a solid line, right? Because we have our inclusive inequality going here. I'll label this down here, y is less than or equal to x plus 1. Once again, you could think about it in terms of the inequality is not opening up to the y, so the y on the graph itself should not be in the shaded region, so we should be shading down here. Or formally, you can talk about the test and once again pick 0, 0 because that's a point not on the line and plug it in. Is 0 less than or equal to 0 plus 1? Is 0 less than or equal to 1? The answer is yes. So the origin is in our shaded region. Awesome. So our answer is where there is the overlap. So the overlap would be in here. And we said, hey, we're also going to write an S because it's S for solution. And that's it. Let's take a look at 2. We'll start off same idea. We have a dotted line for the first one. Y is less than x plus 1. We have x plus 1 again, right? So 1 as our y-intercept. Our slope of 1 is up 1 to the right 1, or down 1 to the left 1. This time, this one's a dotted line. Okay, and we can label it up here. In terms of shading, okay, you can use that little trick. Once again, we're opening up away from the y, so we're going to go away from the y here. That is labeled on the actual y-axis itself. Or you could do your formal test. And we know just from the last one, when we plugged 0, 0 in, this is the same, almost the same inequality, right? That 0 is less than 0 plus 1, 0 is less than 1. Yes, that makes sense. So the origin is on our shaded side. Then also, this is going to be a little bit more work because now we have an inequality in standard form. What we could do is subtract 3x from both sides and try to solve this. I'm going to run out a little bit of room, so I'll do my best. We're going to have 4y is greater than or equal to negative 3x plus 12. Divide everything by 4. And we get y, and we don't need to flip the sign because we divided by a positive, is negative 3/4 x plus 3. So 3 would be our y-intercept. Our slope is negative 3/4, which could be down 3 to the right 4. Or it could be up 3, which goes off our graph, to the left 4, which would be approximately all the way up there. This is a solid line, right, because of our inclusive inequality. Do your best on the line bit, okay? Solid line, and it's basically already labeled right there. I'm just going to draw a little arrow just because I'm running out of some space. The inequality opens up towards the y itself, so we should be shading towards the y up here. Once again, you could always test and say 0, 0 is not on our graph, so we'll pick that. Nice and easy. Is 0 greater than or equal to negative 3/4 times 0 plus 3? Well, anything times 0 is 0, so is 0 greater than or equal to 3? And the answer is no. So the origin is not in our shaded region, which our trick works for that there as well. It takes care of that. Our solution is where they overlap. Great. Let's take a look at a few example problems from real world things. All right. We have an example that's walked through here is that we have a gem company produces necklaces and bracelets in a 40-hour week. The company has 400 gems to use. A necklace requires 40 gems and a bracelet requires 10 gems. It takes 2 hours to produce a necklace and a bracelet requires 1 hour. How many types of each can be produced in a week? And so we need to create 2 equations. And so just real quick, the first piece here, it says N is the number of necklaces, P is the number of bracelets. That first piece there just solely signifies, it says the number of necklaces has to be greater than or equal to 0. Another way to say both of these here is that it says can't be negative. That's what greater than or equal to 0 mean, because it wouldn't make sense to have the number of necklaces and bracelets that you produce be negative. You can't produce a negative number of them. Okay, so the first equation here has to do with the hours, right? 40 hours in a work week. We know it takes an hour for a bracelet and 2 hours for a necklace. So we're saying we have a restriction on the number of hours. We have to be less than how much we work. And we also have this one is talking about the number of gems. 10 gems for a bracelet, 40 for a necklace, right? And you're able to see over on the right side, the graph's already there, and we have our double shaded region is already, they just left that as the only shaded region. So all of those points within that shaded region represent the number of necklaces and bracelets that can be made with a 40-hour work week and 400 gems to use in a week. Okay? So we're going to do one ourselves. Mr. Flowers is on a restricted diet that allows him to have from 1,600 to 2,000 calories per day. His daily fat intake is restricted between 45 and 55 grams inclusively, which means that all this inclusive, remember, that just means that we can have 55 and we can have 45. What daily calorie and fat intakes are acceptable? So we don't actually need to make equations here in this case because of what was given. So I'm going to start here with the 1,600 to 2,000 calories. So on our graph itself, we can go from 1,600, okay, and we're going to look at this and say, all right, well, halfway between 1,000 and 2,000 is 1,500. So we'll say 1,600 is about here, okay, and I'll label that in a second, but we'll say here's 1,600. Mr. Flowers needs a minimum of 1,600 calories and 2,000, right? Because that's already labeled on our graph here, right? But that was told he needs to have from 1,600 to 2,000 calories. So anywhere in between there would work, right? So this is our solutions for the number of calories that he can have, right? Then additionally, he can have between 45 and 55 grams of fat, right? So 45 would be here, and 55, we can label that as well, especially since they're important specific numbers that we need, right? And this is what they would look like on the graph. And we're saying anywhere between here and the fat grams intake would work. So knowing the two restrictions, right, we could then say, where's their overlap? That means anything within here itself would be what he could have to eat, or what is acceptable. So not much to do because it didn't ask us to write an actual equation out, but in terms of a context of the situation, right, take both pieces there and put them on the graph because the graph was already given for us, and we can just say that since they gave us the range, we can put those ranges on and see if there's an overlapping space.